In AP Chemistry, we have focused on the fundamental structure of the atom and its subatomic particles. We have also focused on the periodic trends and behaviors of these microscopic particles in an essence to grasp a better understanding of the chemical relationships and reactions in our world. In this video, we will be going over quantum mechanics, which is a field on the microscopic scale dedicated to the study of particles and probability. Quantum mechanics is built on the foundation of general chemistry and physics, heavily relying on the positioning and movement of subatomic particles. In order to understand the foundation of quantum mechanics, we must look at the things from a different perspective. All of the objects we see in our everyday lives must be viewed with wave and particle-like behavior. Quantum mechanics has led us to a deeper understanding of the atom and the universe with discrete analysis and measurements.
In quantum mechanics, it is a fundamental concept to understand that the position of particles is never definite, but probabilistic. This is given by Heisenberg's uncertainty principle, a theory that, at first, startled many physicists and chemists due to its anomalies. Because of this, Einstein did not agree with quantum mechanics. In the 1900s, the Bohr-Einstein debates were held, which were a series of public disputes about quantum mechanics between Einstein and Niels Bohr, a strong advocate to the quantum field theory. Einstein said that Max Planck's discovery of quantization would require an entire revision on physics, yet he used the idea to support the photoelectric effect, an experiment that we will explain later. Einstein disagreed with the idea that atoms float around a haze of probability rather than a single space in time. In his Copenhagen interpretation, Niels Bohr took this to mean that the physical universe is indeterminate and fundamentally probabilistic. Einstein disagreed and quoted, "God does not play dice with the universe." If quantum mechanics is correct, gravity wouldn't work the way Einstein predicted it to be. The curvature of space-time would be probabilistic. On the other hand, if Einstein's general relativity is correct, then matter couldn't fluctuate so wildly. Chemists and physicists are working together desperately to find a way to reconcile the two concepts.
Quantum mechanics comes from a multitude of experiments tested by many chemists and physicists, not just one great scientist. We will be focusing on some important experiments and how they lead to quantum mechanics. Quantum mechanics begins with the mystery of light. In the 18th century, many people thought light behaved as a wave. However, as research has progressed, further discoveries have proven that light also behaves like a particle. For example, scientists like Arthur Eddington have gone out to explore the properties of light. He concluded that light can bend around massive objects due to a light's particle-like behavior, fluctuating around the bends of space-time. In summary, light behaves like a wave and particle, and the wavelength and frequency of light represents different properties. We have performed calculations relating to wavelength and frequency with atoms in our AP Chemistry course. Furthermore, chemists and physicists have found that the superposition addition of light waves results in a much higher light intensities. They have also found out how wavelength represents light color. There are many forms of radiation, such as X-rays, gamma rays, alpha rays, and visible light. The color spectrum helps us see the progression of color with light. It ranges from infrared to ultraviolet, but the human eye can only see what is in between. As you go from infrared to ultraviolet light, the wavelength of light starts to decrease. We can easily see this by this diagram. The wavelength of certain colors are represented by common objects we are familiar with. The diagram also shows the temperature an object would have to be to emit that color.
The discovery of the theorized black body created a foundation for quantum mechanics and sparked further research into its properties. A black body is a pure black object due to absorption of all light. Black bodies are used to show color by absorbing thermal energy to re-emit light by glowing. Light due to reflection is dependent on the material and size, whereas light due to energy conversion is completely independent. This allowed chemists and physicists to easily analyze color and light. In reality, there is no such thing as a perfect black body, but there are some pretty good examples. The sun is a good near example of a black body. It doesn't reflect any light necessarily, but it emits light from the energy released in its chemical fusion process. Here is a famous graph that shows the color of a black body. It plots intensity as a function of wavelength, parameterized by temperature. The key thing to identify when temperature rises are 1. Intensity rises, 2. Wavelength decreases, and 3. Color changes, moving from right to left on the graph. Decreasing temperature gets you closer to infrared light, while increasing temperature gets you closer to ultraviolet light. Black bodies will continue to convert thermal energy they receive into electromagnetic radiation until the temperature of the black body is the same with its surroundings. In the latter half of the 19th century, a scientist named Rayleigh-Jeans developed a mathematical formula to explain the behavior of intensity as a function of wavelength. His equation says that intensity is always inversely proportional to the fourth power of wavelength. Essentially, as wavelength decreases, intensity increases. However, his equation does not define a definite limit and upper bound. As wavelength approaches negative infinity, intensity will approach positive infinity. This didn't exactly match the real behavior of wavelength versus intensity. This became known as the ultraviolet catastrophe.
Along came Max Planck, a physicist who successfully explained the behavior of this graph. In his offered explanation, he points out how atoms can emit and receive radiation, and he came up with the idea that energy is quantized, meaning that energy comes in little whole packets. Mathematically, that energy value E was based on the frequency value of the wave F, multiplied by some constant h. This constant is called Planck's constant, and you should notice how this number is particularly small. He later mentioned how atoms can absorb 1, 2, or 3 packets, but never 1.5. This can be explained with an analogy. Imagine yourself climbing the stairs. You are gaining gravitational potential energy, but clearly as you go up, you only go up 1 step or 2 steps, but you never gain 1.5 steps. Now let's see what happens if you try to climb half a step. As you can see, it all falls apart. This is an example of quantization. You cannot just gain a portion of a whole step of gravitational potential energy. Of course, some people might argue that if you go up on a slope, like a slide for example, then you would say that the potential energy you gain is not quantized. But imagine zooming into that slide at the microscopic level. At the microscale, that slope would be a staircase, and now you can consider this slide as quantized. You can imagine that there are very, very small steps inside the slide. And that is in essence of what Max Planck was trying to say. Planck discovered a new formula, and we don't have to understand this formula, but it is essentially a reconfiguration of the Rayleigh-Jeans formula. You'll notice that Planck's constant is included as well, and Planck plotted the data, and he was essentially correct. Due to the discovery of quantization, it has helped chemists grasp a better understanding of the atomic model. In the Niels Bohr model, the different principal energy levels of an electron can be represented by a variable n, where n is defined as a set integer greater than 0. These energy levels are integers because they follow the concept of quantization, meaning that just like climbing the stairs where you can't take half a step, you also cannot have an electron possess an energy level of 1.5.
Albert Einstein, another contributor to the quantum mechanics field, developed the photoelectric effect. It started with a guy named Leonard who made a circuit. In this circuit, he set up a photocell and fired a light into it. When light was casted, electrons were continuously moving and spreading out. Due to the idea that wave energy varies with intensity, Leonard hypothesized that if you increase the intensity of the UV source, then surely the electrons would have more kinetic energy. He was wrong. In fact, by increasing intensity, more electrons got released, but they were no faster. Einstein came along and concluded the following. By using Planck's idea of quantization, Einstein thought the light as discrete singular ejected electrons known as photons. That means that when you increase intensity, you are increasing the number of photons or ejected electrons. Light, in the wave sense, will also determine the speed of those electrons. More specifically, smaller wavelengths will result in faster moving electrons. Einstein encapsulated it into a simple statement. If we assume that light is a stream of discrete parcels of energy, and the energy of those photons is proportional to the color of light, we can easily explain the observed threshold. Photons below a certain frequency don't have enough energy to knock out any electrons. In fact, we've done many practice FRQs in AP Chemistry to show this.
With all these principles combining quantization, wave-particle duality with light, and the uncertainty principle, a new era occurred for quantum mechanics, briefly mentioned earlier, the quantum field theory. Quantum field theory has served as a foundation for developing quantum theories about four fundamental forces in nature: electromagnetism, the weak nuclear force, the strong nuclear force, and gravity. Quantum field theory has been successful in creating subtopics for the first three, but, as of today, cannot explain the quantum theory for gravity. Quantum field theory is built upon tight relationship between physics of atomic-like particles. This concept has helped us discover the existence of new particles, such as the Higgs boson particle, an elementary particle discovered in 2012.
Quantum field theory has allowed scientists to continue to branch their knowledge of chemistry and physics into many different phenomena and theories. Quantum field theory has brought us string theory, which is a theory that assumes that all atoms themselves are composed of even smaller, microscopic cosmic strings, which create the fundamental properties of an atom. Further advancements into quantum mechanics and quantum field theory can immensely help us optimize our resources and efficiency and technology. For example, quantum field theory has introduced quantum computing, which is the process of integrating entanglement and wave superposition to develop quantum bits, otherwise known as qubits. Qubits, unlike regular bits in computer science, can possess a value of 0 to 1 simultaneously. Now, with this in mind, a quantum bit is said to be able to store a lot more information compared to a classical computer bit.
All of these theories are mere assumptions based on thought experiments and relationships to other phenomenons. While they provide insight towards a larger understanding of our world, it is up to future generations of scientists to carry on these studies and provide more in-depth explanations to prove their success. The nature of our universe is shadowed in mystery, and it is up to us to uncover these anomalies.